Hello everyone. In this video, we will make a maze solver, and the main logic behind it is to use the A-star algorithm path planning, the A-star path planning algorithm. And the main idea is that we basically build a maze and then we give the robot a start and an ending position. And the robot should be, able to navigate or find the correct path out of it, right? So let's heat it up. Let's create a notebook for solving a maze. So we will create a maze and create the environment. We will solve it using A-star algorithm. Let me connect to our robot environment. Okay, let's just import all of the libraries that we need and connect to the PyBullet. We will import the time. We will import random because here's the thing, we will make the maze creation modular. So we will pass two arguments, right? So the width and height of the maze, and then it will be randomly generated. So no worries about it. We import the system module. Okay, now we have imported all the libraries that we need. Let's connect the physics client. Let's do the other settings as well. Okay, so we just created some basic stuff. We set the gravity, set the time step, and loaded the plane. Let's run that, and it should be there. Okay, now let's do this. No, let's write the logic to generate the maze, and also we need to draw the maze. So that it can be fed to the A-star search algorithm, right? So we have two functions here, as you can see. The first one will basically make the maze, right? And what you need to pass in the width and the height to it, you'll get the string that is basically a maze, right? It will be ASCII maze as a string. And the next function is basically to draw the maze, and it will eventually draw one or two set of the positions. So as you can see, for a demonstration, I have the maze width and height here as 8 by 8, and I just create it and print it here. Next is the step where we will, basically build this whole maze in the PyBullet. And for that, I have defined some parameters like the wall height and wall thickness, and I get this maze string, right? So I strip it in the lines and get the width and height of this of the maze, and then create the maze grid. And the wall color is kind of blackish. So when you have point two and one, it's kind of an dark gray kind of color. Now we will create the collision shape and the visual shape for the vertical walls, horizontal wall, and the pillars. Okay, as I have discussed. So why do we need vertical wall, horizontal wall, and pillars? Is because, for example, if we have this dot dot dot, we are actually having them as vertical wall. If we have longer these dashes, then we are using them as horizontal wall. And when we have plus sign, then we are treating them as pillars. Okay, let's create the walls first. Okay, so as you can see, we have created a template, vertical wall and horizontal wall, and also the pillar. Now it's time that we iterate through all of the lines that we generated here. And we basically fill in all of these guys with the pillars, vertical wall and horizontal wall. So let's iterate through them. Let's iterate through their row and also their column and build whatever we need. Okay, as you can see, I'm iterating through the row index first, and then I'm iterating through the column index first, right? But it's basically the same stuff that we are doing in the nested loop to go through each of the points in a grid. And as you can see, I'm getting the X, Y, and Z first using the tile size. And then if there is nothing, right? And then we are also assigning nothing here. And the if the maze grid shows some stuff, we are trying to build something. So you see some gaps here, right? So there is, if you zoom in here, there is some gap between a plus and a dash, right? When there is a gap, it will not create anything. So in the map or the pivot, you will see a space. There will be nothing, right? There will be uh, a little bit free space between the pillars and the walls, but it will be compact enough. So when you have something like this, then you create a vertical wall, right? When you have something like this one underscore, or you have very small dash, then you create a horizontal wall. So guys, I'm sorry, previously I described this one, the bigger ones, these ones as the horizontal wall. So it's not like that. This one will be vertical walls and this one will be the horizontal ones as it is like that, right? Now, and then if it is a positive, a plus sign, then it's a pillar. Okay, let's just run it, and then we will see that the maze is there, right? We also need to update the camera. Wait a minute, let's also update the camera, right? So center X, and that is actually given by the width multiplied by the tile size divided by 2. Perfect. Then we have the height here for Y. Okay, now the camera distance. Okay, the camera distance will be the maximum between the height and the width multiplied by the tile size. And let's keep an aspect ratio around, not aspect ratio, but a ratio around 0.8. So multiplied by 0.8 and multiplied by tile size should be good. Okay, now that we have this thing, we can reset the visualizer camera, right? Now, at the moment, it is looking like this, right? We want to look it from top. So, by bullet, reset, debug visualizer. Right now, let's select the camera distance. This is given by cam underscore dist. The camera yaw. I ain't giving anything here. Then I need camera pitch, which can be minus 989 here. So guys, these values are actually tested already. So that's why I'm able to paste it. I failed it thrice before doing that. So yeah, I mean, before finding the perfect numbers. So camera target position, but this is a straight away calculation, right? The thing that I did hit and trial is the camera pitch. So 89, 90, it doesn't matter. It's kind of looks the same. And you can also spawn it, right? You can also spawn it and then you can extract the angle that you need. So center X and center Y, and then 0. This can be the target. So we will try to look at the target of the maze that we create. Okay, let's see if the maze is getting created or not. Okay, let's go and see it here. Okay, so it is getting created for sure, but I see some problem, guys. Can you see that? We thought that it would be of dark gray or blackish, but it turned out to be white. Okay, how? Okay, there is one argument missing. Okay, there is one argument missing. So 0.2, and then it is opaque. Now it should be fine. Okay, wait, let me restart this guy. Okay, now let's go here. Okay, perfect. As you can see, it is being developed now. Okay, that looks like our maze, right? So, guys, what we want here is that the robot should go from this position to, let's say, this position, right? That's what we want. Now, let's write a program for the robot to first load here and then give it a target and use the A star for the robot to reach the final destination. What we did here is that we tried to find the start and goal in the maze using the node. We checked if it is free, right? If it is free, if the first node is free, then we are assigning it to be the start node. And also the last one, if it is free, then we assign it to be the goal node. So it's pretty simple. Now, let's go on forward. We have the start and the goal right now. And after that, we need to solve the path. Now, to solve the path, let's say we have the path, oops, path grid, and we need to use the A star algorithm here. So A star, and in the A star, if you remember, we need to first feed him the map. The map name is maze grid here. Oh, wait a minute. This is maze grid. Yeah, that's this one, right? With the zeros that we created. That's the NumPy array. Okay, but search, and we need to provide the start node and the goal. So we provide the start node and the goal node, and we'll have our path here. Now the thing is that we'll have our path here as a NumPy one in the image, right? We need to convert them to the real world, right? Okay. Now it may happen that there is no path found. So there is a faulty maze or something like that. So just print that, hey, there is no path found. Else, if path is found, we need to get all of those guys. So let's do that. So if no path is found here, then I just straight away print, hey, no path is found. However, if it is found, then we just iterate through all of these uh, coordinates that it generates, and we paste them into a list of column and rows in a variable called path xy. Now we try to draw the maze, right? That's why this function was created. So but the thing is that if it fails to draw the maze, we would do nothing, right? That's why we are using try and exception here. So print draw maze. It gives the string. and it will give you the list of the path. So what this one will draw if it works, right? Well, if it did work, I know, because the function works. What it will print you is the path that is generated. It will draw the maze because we pass the ASCII maze as string, and it will draw this path with hash, right? If you check that function, right, draw maze, it will basically draw all the. Okay. However, if it's not able to do that, we will also not bother, right? So we throw exception, we just pass it. So it's not anything that is, creating some problem. So now the thing that is very important is to convert all of this XY inside the path to the real world so that we can move the robots. Okay, so let's do that. So we just initialize an empty list and iterate through all the path XY and multiply it with tile size. Now the tile size is nothing. It's just a converter between the virtual map that we are feeding to our A-star algorithm and to convert it back to the real environment, right? So that's how we append the real world coordinates. So this real world is WX and WY. We get the start real world coordinates and the goal real world coordinates again from path world. The first and the last coordinates are the start and the goal consecutively. Next, when we have the start and the goal, let's do this, let's load um, the markers. So let's load the start marker with green and the goal marker with the red. Okay. Let's also load the robot. Okay, so now you can see that I just marked whatever is there at the start with green color, and red color is the goal, right? And I loaded the robot as well at start position, obviously, right? Okay, next, we need to control the robot. And for that, we need the indices, right? We need right wheel joint index and left wheel joint index. Okay, then we also created this function to normalize any angle. This is important, because we will calculate the direction in which the robot will travel, and it had to be in a range of minus pi to plus pi. Now let's write a function that will calculate distance between 2 points. I added two functions here. One is that calculates the target angle, and it's the same old formula. This is target position minus the current position, and it takes the tan inverse, right? The same formula I'm repeating again and again. And another function that calculates the Euclidean distance between 2 points. And now I will start navigation. While navigation, the main thing is that first thing is that we initialize the tracking variable, which is, let's say, the previous post, right? That we need to do, and then we need to iterate through all of the world points. So let's see how do we do that. Okay, we take the previous pose as a record. We'll use it later, and we iterate through all the path world that is there. So these are the real world coordinates, right? Now we see that if the distance between two corresponding, not If the distance between two consecutive wall points is, let's say, 1 centimeter, right? We just skip that thing because it doesn't make sense to, stay at the same position and just hear about it just moves. Otherwise, we do target a target pose, right? Now, when we have the target pose, we first need to reach to that target pose, right? The idea is to generate the wheel velocity to reach that target pose. So let's start to write the loop that will make us to reach the target pose. Okay, so inside the loop, let's see what I have done. I took the car position and orientation, and also I took out the yaw angle, which is basically theta that we were using, and also the current pose from the real robot, right? That's the 3D pose that we need. We get it into the list. This is for tracking that we are doing. So when we will move the robot, we will draw some lines. Uh, so through the path, so that we know how the robot actually reached there. Again, if we see that the distance between the current pose and the target pose is less than zero point 0.2 meters, then we basically break this loop and we go on for the next target pose. That's the idea. Now, we calculate the target angle between the current pose and the target pose. It is pretty normal. We calculate the angle error and the base speed, which I just keep it to 12. If you make it high, then it may happen that the robot will topple due to the physics applied in it. And as you can see, I calculate the absolute error. So if it is more than 0.4, right, then it calculates the left velocity and right velocity straight away using the turn gain. And if it is less than that, then it is using the base speed, right? The idea is that if it is more than that, then you have to turn. You don't need to travel straight. Now, I just use the left and the right wheel velocities to move the robot and step simulation. So after that, when we reach the last target, we need to stop the robots. To stop the robots is easy, just to pass the velocity as 0. And then I just print, okay, the goal is reached. Okay, let's see and run this, and I hope it should work. What's the situation of the simulation environment right now? It is like this. Okay. Whoa, okay, it is flipping a lot. Okay, let's see what goes on here as soon as I run the simulation. Okay, it says no path found at the moment. Okay, let's run this guy again. Okay, wait a minute. Let's run this guy from start again. Shouldn't be that case actually. Okay, I think it said no path found again, right? Okay, let me debug what's the problem here. Okay, guys, there was a subtle mistake and it was failing silently. So the bug was that I was pulling wrong line here. So there should not be any one index here actually. That was the thing that was basically creating the problem. Let's run this guy again and see if it fails again, or if it runs. Okay, now it's a maze and okay, this looks better. Still, it's not going right. Maybe there is some error, is there? Yeah. So math is not defined. Okay, let me define math. Let me also close this and restart it. Okay, so let's start it again now. It's already being restarted, and I tried to import the math library. Okay, seems like it's building okay now. Seems like there is more problem. Okay, wait, there are more problems. Let me go through it. Ah, no, guys, it is running, it seems. It is very, very slow. I think in my PC it's slow because it's a very, very old CPU. And if you have a GPU or else your CPU is much more powerful, has is basically i7 or i9 processor, then it will be pretty fast. The PC that I'm using right now is i3 processor and it is pretty slow. And we cannot expect more than that. So unfortunately is the case. Normally the simulation also reflects if you have a GPU, then the pipelet will be connected to the GPU automatically, and the simulation will be much, much faster. Okay, so at the end, we are able to reach the goal of the maze. And it says goal reached. Let's disconnect it. So the goal of this lecture is finished. We have created successfully a maze solver. And I mean, you can literally create your own maze. So what you need to do is to change these matrices here, 8 out of 8, 8 and 8. So if you set 100 and 100, then it will create a very, very big maze. And I don't know when the robot is going to travel that. Maybe what you need to do is, um, tune the speeds a bit so that it is able to handle that. So with that, we will see us in the next video. Bye bye.